Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, I want to talk about a game of power series. And this conversation is actually very much related to work that you're doing in your Calc 2 class when you're working with representations of functions as power series. Specifically, representations of functions of power series that revolve around the geometric series. So this is all based upon the following. There we go. So this entire game of power series is based on when you're working with the power series n equals 0 to infinity x to the nth, which we know converges as long as the absolute value of x is less than 1, and we know it converges to 1 over 1 minus x. That's both from our pre-calculus and from our Calc 2. The problem is you're given a lot of terrible functions and you're asked to find their power series representation, and it's really hard for some students, and actually for me, to be honest with you, to rebuild a power series based upon a function that's handed to us. For example, if somebody hands me the function, and I created a video for this, so I'm not going to do this one here, but if somebody handed me tan inverse of x, and they said, what's the power series for that? Or if they handed me a function, natural log of 1 plus x, and they said, hey, I need another power series for that. Or if they hand me, I mean, there's a whole bunch of them, right? So if they hand me, I don't know. I had one in my lecture notes today. So negative 8x to the 7th over the quantity 1 plus x to the 8th squared. Okay. So stuff like this. Remember, when you're trying to work and rebuild power series or build power series for a function, you need to somehow get your function to look something like this. And unfortunately, each of these is very challenging to rewrite as 1 over 1 minus x. It looks near to impossible. So the whole point of this video is to give you a way to really envision how to do that. A really nice codified way of approaching these. So what I'm going to do is I'm just going to rally these guys up, move them off to the side, or maybe I'll just line them up here like this. And I'm not going to work with any of these because I'll have extra videos showcasing this method. But what's important is I want to really build the method here. And then that way in my other videos, when you're watching like me building power series from functions, when I use this method, you don't have to say like, what the heck is he doing? Instead, you just watch this video once and you're like, oh, wow. Okay. That is useful. I do have to say, I just created this morning, and I think that it is going to be very useful. So let's get down to it. All right, we'll start with just a table. And this table has two columns. It has a function world column and a power series world column. And actually, this idea of having different worlds in mathematics, different types of worlds we want to work within, is going to be very important as you move forward, because the reality is that when you move into differential equations, for example, you're going to want to work in a world by Laplace. It's called a Laplace transformation or a Laplace transform. And what you do is you transform a really hard problem from differential equations into a different world, and it becomes an algebra problem, much easier to work with. So if we can step into different worlds to work on something, whatever it may be, and it makes it easier to do that, then more power to us, right? So now what I'm going to do is I'm going to list down in the 3 rows that I have here the names of the function, the derivative, and its integral. That is, the middle row I'm going to call f of x, and in fact I'll use blue for that. The bottom row I'll call f prime of x, and the top row I'll call the integral of f of x. Now, generally speaking, you're starting in that middle row. Somebody hands you a function, they say, I need to find the power series representation of that function. Like these three functions up above, somebody hands me a tan inverse or a natural log of 1 plus x, or an h of x is equal to negative 8x to the 7th over 1 plus x to the 8th squared. So that would be my original function. So I'm going to start here. And if I want the power series representation of that function, then I definitely want to end over here. Now I call this the game of power series because there are some rules to this game. There's actually only one real rule to this game. The one real rule is the following. You cannot do things diagonally. You'll see what I mean by do things in a moment. So the one rule is don't go diagonally. So somebody hands you a function and you want to arrive at its power series. If you can't go diagonal, then all you can do is go left, right, up, or down. So you start with a negative 8x to the 7th. It's just terrible. Negative 8x to the 7th over the quantity 1 plus x to the 8th squared. That's what you want to find the power series for. Well, you have a choice. You can either go to the right. Well, if you could immediately go to the right, if you can immediately find the power series for that, this would not be a hard problem. It'd be incredibly easy. So that is not going to be viable. It's an option, but it's not realistic. Or you can go down and take the derivative of this function, or you can go up. You just can't go diagonal. So you can either go up, down, or to the right. You eventually, through movements, want to arrive at the end. So it's one of those two paths, either up to the right and down or down to the right and up. Those are the two kind of moves you can make here. Whatever move I make, I need to make a move so that I can find the power series of the function after that move. For example, if I decide to go down, and notice I'm using red because I know it's a bad idea. If I decide to go down to take the derivative of this function, well, that means I would take the derivative of this function. Now, if you want to, you could try to clean that up and see if you can create a power series out of that. But I'm telling you right now, I don't think you're going to be able to create a power series out of that. So not only was it just a challenge to go from the original function to its derivative, but once we arrive at a derivative there, it's not going to be very useful because we won't be able to transform that into a power series. So this is what I would call the hard direction. And just like you want in a lot of avenues, you want to take the path of least resistance. And there's a lot of resistance taking the derivative here. So let's see what would have happened had we gone up. And by the way, this kind of coincides with how I think about the ladder of calculus, where going up is integrating and going down is differentiating. I have a video on that if you really want to see it. You don't have to though. All right, let's go ahead and integrate that function. Now that I'm going to go ahead and do down here, the integral of negative 8x to the 7th all over 1 plus x to the 8th squared dx. Well, if you take a look at that, a little u sub action will be very helpful. Let u equal 1 plus x to the 8th so that du will steal away an 8x to the 7th dx. Well, great. I have an 8x to the 7th dx to steal away. So this means this is going to be the negative integral of 1 over u squared du. And the antiderivative of 1 over u squared is a negative 1 over u. So this is going to be a negative negative, or basically just a 1 over u plus some constant of integration. Remember what u was? U was 1 plus x to the 8th. So it was a very quick antiderivative, and the antiderivative actually is 1 over 1 plus x to the 8th plus some constant c. Great, that was pretty easy actually. So maybe I could transform that into a power series. And absolutely I can. The 1 over 1 plus x to the 8th can be written as 1 over 1 minus a negative x to the 8th, which is the power series n equals 0 to infinity of negative x to the 8th to the n. And of course that cleans up. And so I happen to know the power series is very clean. Remember, we still have a plus c there, but let's go ahead and plug that in. We have a c plus the power series summation n equals 0 to infinity of negative 1 to the nth, and then x to the 8n. Let me just double check that I'm right. So far, so good. Now, that was pretty easy as well. Remember where we want to end. So part of our game is just driving to this ending part. And if you think about that, the higher you are in this process, the higher you are in this ladder, if you will, the higher row you're at, then to get to a row below that, you'll have to take a derivative. So let's go ahead and take a derivative to go down to this ending point. The derivative of c is 0, and the derivative of a summation, and I'm going to write n equals, I'm not going to fill that in, but the derivative of this sum, well, let's see, we have negative 1 to the nth, that's just a constant, times the derivative of x to the 8n is 8n x to the 8n minus 1. Now here's the deal. Something I tell my students is that you need to double check to make sure that you don't need to reindex this right here. When n is 0, you'll see the very first term in this series is actually 1 times x to the 0th, or 1, and then plus, and then you have some other terms in line, right? When n is equal to 1, it's actually in minus x to the 8th, and then plus x to the 16th, and so on and so forth. So that very first term, when you take its derivative, it will disappear. So our series does not start at 0, it's going to start at 1. Again, the very first term of this power series is going to be a constant. And when you take the derivative of a constant, it will disappear. So instead of starting at n equals 0, our derivative will start at n equals 1. And we have suddenly arrived at the end of our problem there. Very, very nice. And this is how I envision all of the function representations or representations of functions as power series problems working, is that it's a little puzzle and you have a starting point and an ending point, and you just have to figure out what the right path is. A little heads up, you might have to go down 2 rungs, for example. So sometimes you'll start at some value and maybe you need to take 2 derivatives to get to something that's workable. So having 3 rungs or 3 rows here is important to start with, but you might have to increase the number of rows so you can climb higher or go lower in this process. But that is the game of power series, in my opinion. Now, I do want to let you know, if you're watching this while you're learning function representations of functions of power series, you are eventually going to learn something called Maclaurin and Taylor series, where you can derive power series for almost every other type of function. But this is still a great concept, and it still will be very, very helpful in the long run. So I recommend trying your hand at this, using this idea a few times, and you might find that it makes your life very nice. All right, I hope this is helpful, and I hope you have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.